All right, guys, so we're going to look at extreme value theorem to begin off Unit 5 here. And as always, we'll start with the bell work, so give it a pause if you haven't tried it, and then check back. So this is obviously one that's got a lot of different possibilities here, but when we did this, what one of my classes came up with was things like the most of something, exaggerating, a very large quantity above a previous set standard, something that was dangerous. Okay, those are some of the different examples. When they came up with their predictions, I hope you got something somewhat similar, but what we had is proves the validity and existence of extrema, or to exaggerate some mathematical equation to find maximum and minimums. Now, the truth is, are these exactly right? No, but this is sort of the idea, is just to get you to start thinking about these things and try and figure out what they might mean, which is the whole point. So then let's jump in and let's actually define what exactly well, let's get started, I guess, by defining a relative and absolute extrema of a function. So first of all, relative extrema, or points on a graph of a function where the function changes from increasing to decreasing, or vice versa. An absolute extrema are the highest or lowest points on the graph of a function. Okay? Biggest difference there is going to be that our absolutes can actually be on our endpoints, whereas our relative obviously can't be. We're going to see that in action as we get going here. So here, pictured below, we've got our graphs of f and g. Let's start just by looking at f. Identify the coordinates of the relative extrema. Well, we're going to have relative extrema anywhere that there's those min or maxes. Let me actually make that a little bit bigger. There we go. And so we're going to have two relative mins. If we look there, we're going to have one here and one here. So that is at -3, 0. And we're also going to have one at 2, -6. And we'll have one relative max as well. Our relative max is the one that's up here, and that's at -1 and 3. Now, on that domain of f, what are the coordinates of the absolute extrema? So on our domain, right, that's unrestricted. We haven't restricted the domain in any way, so it's on all possible values of x. And so what that means is that we will have an absolute min at the lowest point, which is this one right here, so 2, -6. But for an absolute max, because the function goes up forever, it's got those arrows, that means we won't get one. We're going to get infinity, which means there isn't one. Okay. Now let's jump over. Let's look at g for a second here. So we want to know the relative extrema. So let's start off once again with our relative mins, which are going to be here and here. So we've got -3, -4, and we've also got 3 and 2. Now, our relative max, we've got a single one. That's that guy right there. And that's going to be at -1 and 4. Now, same kind of idea. If we look at the domain, this time our domain does have an ending. It doesn't just go on and on forever. So it'll be a little bit different. So let's start by looking at our absolute minimum. Well, like last time, in this case, the lowest point this ever gets to is right here, which is at -3, -4. Our absolute max, on the other hand, is going to be different. Well, obviously, because it has one. And so as much as you might think, oh, it's here, it's at 4, this endpoint is actually at 5. So that's going to be our ab max. Okay, because remember, the absolute maxes can be on the endpoints. So this point here was at 6 and 5. So on the domain of our given function, did the absolute extrema occur at the relative extrema? Well, sometimes, right? So the absolute minimums were, one of the relative minimums. but our absolute maximums did not relate to the relative maximums, right? Now that's not a rule, right? That just happens to be for these particular functions. But the idea here is that you understand the absolutes could be relatives or endpoints, okay? So let's take a look at a couple other examples here. And this time we're going to actually restrict our domain. So on the interval -2 to 3, so let's go ahead and draw that in. So we're going to do it from like here to here, okay? What are the absolutes? Well, our absolute minimum is the lowest possible point it gets between there, which is going to be right there. And so that's at the point 2, -6. Now our absolute max, right, it could be our endpoint, but that's lower, so up here. So the highest one is going to be right there at -1 and 3 because it is higher than either of our endpoints. Now we're going to look at a different interval. We're going to go from -4 to 1. So I'm going to do that in different colors so we can see it nice and easy. So now we're going to go over here, -4 to 1. And so now when we're looking at our absolute minimum, the lowest point is actually going to be right there on the endpoint. So our absolute minimum was at the point 1, -3. Now for our absolute maximum, we have to go take a look. And if we're looking on that green one, this is pretty high, but if we look here, the endpoint here looks to be higher. I think it's actually right there. It's kind of hard to see it, isn't it? Yeah, let's go with 4. I think 4 is more accurate. So that's going to be at -4 and a height of 4. All right, let's do the same kind of thing over here on g of x this time, where we've got that same function. But we're going to continue to restrict our domains. So we're going to look at -4 to 5. Now, if we're looking at that, our absolute minimum, this is the lowest it ever gets on that interval. So that'll be at -3, -4. But when we talk about our absolute maximum, well, we've got this point and that point that are both at the same height. So we actually need to list both of them, -1 and 4, as well as 5 and 4, to get our two different absolute maximums. Then we're going to switch our interval and go from -2 to 6. Like so. And then when we're looking at our absolute minimum here, it's pretty easy to see that it is right there at our endpoint where we hit 0. So our absolute min is therefore going to be -2, 0. And our absolute max, again, because we're going all the way to 6 here, is that other endpoint. So in this case, the relatives were not part of it at all. Again, not a rule, just that we need to remember to check endpoints and also the relative points. Okay, so when the domain is restricted to a particular closed interval, what 3 places do we need to check? Well, the first one that I've been mentioning a few times is endpoints. This is what's different than everything we've done before. We usually don't include endpoints. For extreme value theorem, we do. The other ones we need to include are going to be our relative extrema. This is where f prime of x changes sign. And the third one is going to be where f prime of x is undefined. Because remember, just because we changed our definition, I guess, of relative extrema, that they were where the derivative was equal to 0 or undefined. We changed that last chapter from our original. So those are the 3 things that we need to check. All right. So let's actually write down then what is our extreme value theorem. So if f of x is continuous on the closed interval from a to b, then f of x has at least one absolute max and at least one absolute min or minimum on the closed interval. Okay, so that's our actual definition for our extreme value theorem, what it does. So let's take a look at another example here that's a little bit bigger. So we've got our function right here, f of x, on the closed interval -4 to 1. And the first thing we want to do is find the absolute max on -4 to -1. So we're going to be looking only from here to here. We're not looking at the whole function. We're just looking at that piece. And if we do that, our absolute max is actually these two endpoints. They are the same height. So we would get -4 and 6, as well as -1 and 6. Now, if we're looking for that absolute minimum on that same interval, that's going to be this one down here. So our absolute minimum is going to be at -3, and 2. Then what we're going to do is we're going to look here, we change our interval. So we're still going to go over here from -4, but now we're going to go to 1. So I'm going to have to, I can't even see it. I have to scroll down. So we're going to there, which is all the way down here. So our absolute max, if we look up here, the highest point we ever get to are those same 2 points. So -4 and 6, and -1 and 6. But the absolute minimum is way the heck down here. So our absolute minimum is at 1, -14. All right, so let's use the absolute or the extreme value theorem to locate the absolute extrema on this function of the closed intervals, and we're going to do this algebraically. So we just did it graphically, which means that we can then compare and make sure it's the same. So what we're going to do first is take the derivative. That's going to be -3x squared minus 12x minus 9. Then we're going to figure out where this thing equals 0, which means we're going to need to factor it. So let's take out that -3 to make it easier for us. X squared plus 4x plus 3. Why? Because that's pretty easy for us to factor and get x plus 3, x plus 1, which means that our critical points then are going to be -3 and -1. So what do we need to check? Our endpoints. So we're going to go f of -4. Notice here it's going into f, not f prime. And I'm going to plug that into my original equation here. Okay? You can take a second to do that on your calculator. I'm going to do the same. And when I put that into my calculator, I got that this was equal to 6. Then I'm going to check f of -3, because that was our critical point. And same thing, we're going to put -3 into here. Okay, you're just putting all of your x's become -3s, and we get 2. And then our last one here is to put f of -1, partially because it's our critical point, but also because it's the end point. And so then when we look up here, you're going to put in -1 for each of those, and you're once again going to get 6. That means that this is my ab max, which so is this. So we've got 2 absolute maxes that equaled 6 at -4 and -1. And we got -3 and 2 as our absolute min, which is exactly what we got before, right? -4, 6, -1, 6, and then our minimum was -3, 2. So we got the exact same things algebraically, which is the whole point. Okay. So then over here, this is just a different interval, so we don't need to go through the derivative again. We already know what it was. So we're going to check f of -4, f of -3, and we already know what those ones are. That's 6. This is 2. Then we're going to check f of -1, and we already know what that one is as well. It's 6. The last one that we need to check is f of 1. So we're just going to plug 1 into our original equation here, and then we get our -14. So that takes over as our absolute min on this interval, and our absolute max is still shared between these two here. Okay, so we can see again that if we look up here, it's the same. -4 and 6, -1 and 6 for our maxes, and 1 and -14. So we got the exact same thing. Okay, so whether it's graphically or algebraically, we can now see that we'll get the same. So as we just continue right on, what we're going to look at here is whether or not we can actually use EVT or not. So basically, whether or not it is applicable. All right. So if we look at this one here, okay, and we're looking at -5 to 0, the potential problem is at -3. And of course, -3 is on this interval. Therefore, we cannot use it. So we have to say that EVT is not, well, actually, no, let's just say not applicable. That's faster. Because h of x is undefined at x equals -3, which is on the interval that we have negative 5 to 0. So therefore, we cannot actually use it in this case, okay? If we look at our next one here, this one would have, the front x has no problems. This back x is going to be an issue if it is less than 3, right? And the reason I know that is simply because I know that x minus 3 needs to be greater than or equal to 0, which means that x needs to be greater than or equal to 3 because I can't take the square root of a negative number, okay? And so if I look at that, the issue there is going to be quite similar in the sense that if x needs to be bigger than 3, well, here it's not. It's less than 3. So again, we're going to say EVT is not applicable because g of x was a capital, g of x is only defined on x is, I'm going to leave a space there because I can't actually write that symbol quickly. I don't remember the shortcut. X has to be greater than or equal to 3. Now, if we look at our last one, this is quite similar to the first one where there is a restriction. And what I know is that x plus 7 has to be greater than or equal, no, not equal, sorry, it just needs to be greater than 0. I can't take the ln of 0. I can take the ln of anything bigger than 0. So that means that x has to be bigger than negative 7. And since we are dealing with negative 5, that's okay. That's not going to be a problem on our particular interval. So we can say that EVT is applicable because f of x is defined for x is greater than negative 7, and this is outside our interval. So no problems. Basically, because our interval is within that x is greater than negative 7, we're fine. We have no issues with this. Okay, let's try and apply this to a few more here. Given the functions below, determine the absolute extrema of these functions on that specific interval. So what I'm going to do is, just like most things in this class, I'm going to start by taking the derivative. And that'll give me 3x squared minus 4x minus 3. Now at that point, I want to find my critical points. Those are not going to be easy, so I'm going to use my graphing calculator and find those critical points, okay? When I do so, I'm going to get that x needs to be, negative 0.535 or 1.869. Now you can do that by simply graphing this and finding the zeros, okay? I'm just not going to do that for you because I think you can put that in your calculator and see it. All right, then what I'm going to do is check my endpoints, so f of negative 1. I'm going to also check my critical points, so 0.535, and f of 1.869, and then finally f of 3. And again, you're going to either use your calculator or you're going to, well, either way, you're going to use your calculator, whether you're putting it into this function or whether you graph it and find them. And so when I do that, I got negative 2. I got negative 1.121. I got negative 8.065, and I got negative 2. So the biggest one I have, which is a little bit awkward to realize, is this one. Because even though it's negative, it is the least negative. So it's the biggest one. And this is the most negative, so that is my absolute minimum. All right, let's take a look at this one, and it's going to be quite similar. I'm going to start by finding that derivative so I can come up with my critical points. Careful here, this is a chain rule. So this is going to be 2 sine x times the derivative of the inside, which is cos x. And then I'm going to take the derivative of cos x, which is negative sine x. All right, now I got to figure out when that thing is equal to 0, which is pretty hard unless I factor it. So I'm going to factor out a sine x, and that's going to make it a lot easier. Because then I've got 2 cos x minus 1. And it's a whole lot easier to see these. So this one, we know that sine is going to be 0 at pi and 2 pi and 0, et cetera, et cetera. Now, I'm not including 0 in this case because 0 is outside of our domain, so I just included pi and 2 pi. Now, for this one, I've got that 2 cos x minus 1 needs to be 0, which basically means I'm looking for when cos of x is equal to 1/2. That happens in quadrant 1 and 4. Quadrant Yeah, quadrant 1 and 4. And so I'm going to get that that is going to be pi over 3, which is outside of our domain. Sorry, I should have just seen that. Quadrant 1's not in our domain. So it's actually only going to be the other one, which is 5 pi over 3. Okay, so those are going to be my critical points. So then what I'm going to do is I'm going to check my endpoints and these. And so my first one is going to be pi over 2. So I'm going to find g of pi over 2. Then I'm going to find g of pi. Then I'm going to find g of 5 pi over 3. And lastly, g of 2 pi, which is an endpoint and technically a critical point. Okay, so if we look at that, and I plug those in, and I plug this into the original, sine of pi over 2 is 1, 1 squared is 1, and cosine is 0, so it's just 1. If I plug in pi, sine of pi is 0, but cosine of pi is negative 1. And 5 pi over 3, this one's a little bit more complicated. So let's see, we're going to get sine of 5 pi over 3 is root 3 over 2, which will be 3/4, plus cosine is going to be 1/2. And so together that's 2, we're going to get 5/4. Okay? And then 2 pi, sine of 2 pi is 0, cosine of 2 pi is 1, so I'm going to get 1. So this is my absolute minimum here. And this one here would be my absolute max, because that's a little bit bigger than 1, right? It's like 1.25. All right, hopefully that made sense. But I did like algebraically because I can find it using the unit circle quickly. If you couldn't, look up the unit circle or use your calculator. And then of course, one like this, I needed to use my calculator anyway. All right, let's take a look at this now. So same kind of idea here. I'm going to start by finding f prime of x. Now this is a chain rule, so the 2/3 comes out front. Then I'm going to multiply it by this with the reduced power, which, well, you know what, we'll do it the slow way just in case. So I'm going to subtract it, get negative 1/3, and then I'd multiply it by the derivative of the inside, but in this case, that's just 1. So I am going to simplify this because that's ugly to look at in my opinion, and I'm going to put it on the bottom, and that is the 2 over 3 times the cubed root of x plus 2. Now, that's never going to be 0, but it is going to be undefined at x equals negative 2. Okay, so then I'm going to check my points. So I've got f of negative 3, f of my undefined critical point there, and f of 6, my two boundaries. Now, when I put those into the original up here, negative 3 plus 2 is negative 1. Negative 1 squared is 1, cube rooted is 1. So this is just going to be 1. If I put in negative 2, it's just 0. And if I put in 6, I'm going to get 8. 8, this time I'm going to cube root first because that puts me at 2. 2 squared is 4. So there, 0 would be my absolute min, and 4 would be my absolute max. Again, if you had a hard time following me there, try writing it out step by step or putting it in your calculator. But these are not overly complicated, so you can do them in your head like that. Moving on to our last one here, h prime of x. In this case, remember the derivative of natural logarithm is going to be the derivative of the inside, so 2x, over the original function like that. Okay? Although, that's not going to matter. Never mind, that's not even going to matter. Because if I look at this one, this function is only going to be defined. I know that x squared minus 4 needs to be bigger than 0, which means that x squared needs to be bigger than 4, which means that when I square root that, I'm going to get that we're going to have the positive version, so 2 is greater than, put that backwards, 2 is going to be, x is going to be greater than 2, or x is going to be less than negative 2. I have to flip it because it's negative now. And when I look at this, I'm not dealing with that at all. I'm dealing with negative 1 to 3, so that's not going to work. So I actually, in this case, it's even easier. I can just say no EVT because h of x is not defined on negative 1, 3. So therefore, there's nothing else I can actually do on that one. And that takes us to the end. So go ahead and try those practice problems now if you've got them. And yeah, we'll see you for the next one.